Hello viewers, I Nilofuzargam welcome you to the first part of the new episode on the topic Measures of Central Tendency. In this part, we'll study about the meaning of arithmetic mean, its objectives and its types. We'll also study in the script the various kinds of averages such as arithmetic, simple and weighted, geometric and harmonic means. Merits and demerits of all these kinds of averages are also discussed in this session. We'll also learn the calculation of these averages in case of individual series, discrete series and continuous series. And also the script includes the discussion on the relationship between the three averages, which are arithmetic, geometric and harmonic. But we must first understand the following concepts before proceeding further. Measures of central tendency are numbers computed from the data set that help us locate the center of a relative frequency distribution. These are expressed in the form of averages. There are two main objects of computing a statistical average. One is to give concise picture of a large group to describe a series it represents. The other, which follows from the first, is to afford a basis of comparison with the other groups. It follows that an average may be computed for its own sake or for the comparison of two or more sets of given data. The most popular and widely used measure for representing the entire data by one value is what most laymen call an average, and what the statisticians call the arithmetic mean. It should be noted that the statistician did not like the term average because it has too loose a connotation. It has different meanings. For example, an average person, an average height, and an average income, etc. That is, it can refer to either mean, median, mode, geometric mean, harmonic mean, or any other average. Arithmetic average is so popular that the word mean or the word average alone without qualification is used to denote this particular type of average. When anyone speaks of the mean or the average of a series of observations, it may as a rule be assumed that the arithmetic mean is implied. Its value is obtained by adding together all the items and adding its total by the number of items. In other words, the mean of a set of quantitative data is equal to the sum of the measurements divided by the number of the measurements contained in the data set. Arithmetic mean may be either simple arithmetic mean or the weighted arithmetic mean. Now let's come to the definitions. Simple arithmetic average. It is the average where all the items of a distribution are treated alike, each item being considered only once. Second one, weighted arithmetic average. It is the average where each item of the distribution is assigned weight in proportion to its importance in the series. The process of computing mean in case of individual observation is very simple. Add together the various values of the variable and divide the total by the number of items. It can be represented symbolically as x bar, which is equal to x1 plus x2 plus x3 plus so on to xn. The whole thing is divided by capital N. So that is equal to sigma x, the whole thing divided by n again. So x bar is the arithmetic mean here. Sigma x is sum of all the values of the variables x, that is x1, x2, x3 so on till xn, and n is the number of observations. The formula suggests two steps in calculating mean. The first one, add together all the values of the variable x and obtain the total sigma x. The second point, divide this total by the number of observations. So let's see an example here, example 1. Calculate the mean of the following 8 sample measurements. So 8 sample givens are 5, 7, 4, 8, 2, 9, 3 and 4. So let's calculate that. Let's come to the solution. Given is 5, 7, 4, 8, 2, 9, 3, 4. So we have the summation. We have x bar is given as sigma x divided by n. So that is equal to, we are adding all the values, 5 plus 7 plus 4 plus 8 plus 2 plus 9 plus 3 plus 4. The whole thing is divided by 8. So this is equal to 42 and the whole thing is divided by n, which is 8. So 42 by 8 will give you 5.25. Example number 2 here. The following table gives the monthly income of 6 families in a society. So calculate the arithmetic mean here. Solution. Let the income be denoted by x here. X bar is equal to sigma x divided by n, we know. So we are adding all the values here. So we are getting sigma x equals to 42,000 and n we already have here is equal to 6. So sigma x by n will be 42,000 divided by 6, which will give you 7,000. Hence the average income is 7,000 per month. Arithmetic mean can be computed by x bar is equal to sigma fx divided by n here. Now here f is the frequency, x is the variable in the question and n is the total number of observations. Now let's come to an example here. From the following data of the marks obtained by 55 students of a class, obtain the average marks. Now let's see the solution. Let the marks be denoted by x and the number of students by f. So we have x bar is equal to sigma fx by n. So that is equal to sigma fx will come out to be 2250. We know n here is 55. So we have 2250 divided by 55 and it will give you 40.90. Hence the average mark will be 40.90. In the continuous series, arithmetic mean can be computed by the following method. So there are 3 methods. First one, direct method. When the direct method is used, x bar is equal to sigma fm by n, where m is the midpoint of the various classes, f again is the frequency of each class, and n is the total frequency. We have the second method here, shortcut method. It can be computed by the following formula. X bar is equal to a plus sigma ft by n, where a will be the assumed mean, d is going to be the deviation of midpoints from assumed mean, that is m minus a, n is the total number of observations. We have the other method which is called as step deviation method. It can be computed by again the formula as x bar is equal to a plus sigma ft divided by n into I. So here we have a is the assumed mean, d is the deviation of the midpoints from the assumed mean, that is m minus a by I, n is the total number of observations, and I is the common size, or we can say width, of the class interval. Now let's come to example number 4. From the following data, compute the arithmetic mean by direct method, shortcut method and step deviation method. So we have to use all these methods and we have to calculate the arithmetic mean. So let's see the solution to this. Calculation of the arithmetic mean by continuous series now. The first one, direct method, we have the formula x bar is equal to sigma fm divided by n. So we have calculated sigma fm, which is equal to 3300, and n is 100 we know. So we have 3300 divided by 100, which will give you 33. Now the shortcut method, let's assume a is equal to 35. Now sigma ft is going to be minus 200 and n is 100. So apply the formula. We have the formula x bar is equal to a plus sigma ft by n. So that is equal to 35 minus 200 divided by 100, which will give you 35 minus 2, which is equal to 33. Now let's come to the third one, step deviation method. Now using step deviation method, now let's again take a is equal to 35, sigma ft we know it's equal to minus 20, and n is here 100, I is 10 here. Now let's use the formula. X bar is equal to a plus sigma ft by n into I. So that is equal to 35 minus 20 upon 100 into 10. So that is equal to 35 minus 2, which will give you 33. It may be defined as that average which is obtained by applying weights to the items in accordance with their relative importance. One of the limitations discussed above is that it gives equal importance to all the items, but there are cases where the relative importance of the different items is not the same, where the term weight stands for the relative importance of the different items. The formula for computing this is xw bar, which is equal to sigma wx divided by sigma w, where xw bar represents the weighted arithmetic mean and w here is weights, x is the variable. Now let's see an example here. Calculate weighted mean from the following data. Now let's see the solution. We have this calculation of weighted mean. xw bar, the formula is sigma wx divided by sigma w. So we have already calculated sigma wx, which comes out to be 472, and we know sigma w from the table as 30. So 472 divided by 30 will give you 15.73. Let's see the merits first. First one, it is very easily calculated and understood. Second, it is by far the most commonly used. Third, it is based on all the observations. Fourth, it is affected by the value of every item in the series. Fifth, it is adaptable to algebraic treatment. Now let's see some of the demerits here. First one, since it includes all the items, its value may be distorted by extreme values. Second one, it cannot be calculated if any item of the series is missing. Third one, the average may not coincide with any of the actual items in a series. Now the fourth one, in cases where the items cannot be represented quantitatively but can be ranked, the arithmetic average is not an appropriate measure of central tendency. When we deal with the quantities that change over a period of time, we need to know an average rate of change. It is defined as the nth root of the product of n items of series. If there are 2 items, take the square root. If there are 3 items, we take the cube root, and so on. Symbolically, it is represented as gm, which is equal to nth root of x1 into x2 into x3, so on into xn, where x1, x2, x3, etc. are the various items of the series. When the number of items is 3 or more, the task of multiplying the numbers and of extracting the root becomes excessively difficult. To simplify calculations, logarithms are used, and then the geometric mean is symbolically represented as log of gm, which is equal to log of x1 plus log of x2 plus log of x3 plus so on till log of xn. The whole thing is divided by n. So for this, we have an example here. Supply of machines of 6 factories is given below. Find the geometric mean. Now let's see the solution here. Calculation of geometric mean can be done using this table. So finally, let's put up the formula. Log gm is equal to log x1 plus log x2 plus log x3, so on till log xn. The whole thing is divided by n. So we know this is equal to sigma log x. The whole thing is divided by n again. We have already calculated sigma log x, which is equal to 7.5054. So apply the formula. Log of gm is equal to 7.5054 divided by 10. The log of gm will be equal to 0.75054. So let's take the anti-log of this. So gm will be equal to now anti-log of 0.75054, which is equal to So antilog of this is going to be 5.63. So we have the formula here. Gm is equal to antilog of sigma f log x divided by capital N. Let's see an example here. Supply of machines of 6 factories is given below. Find the geometric mean. Let's see the solution. Calculation of geometric mean here in this table. So Gm is equal to antilog sigma f log of x divided by N. So Gm is equal to antilog of 28.1661 divided by 20. So Gm is equal to now antilog of 1.408305. So finally we have the Gm with us, that is equal to 25.60. Now we have the formula with us for this, that is Gm is equal to antilog of sigma f log x divided by capital N. Now let's come to the next example. Calculate the geometric mean of the following frequency distribution. So let's see the solution. We are doing the calculation of geometric mean by using this table. Then we have geometric mean is equal to antilog of sigma f log x by N. So this is the formula we have. Now we are putting up the values here. Gm is going to be the antilog of sigma f log x. So sigma f log x we have calculated is 82.264 and we know capital N is 68. So Gm is equal to antilog of 82.264 divided by 68. So Gm is equal to antilog of 1.20976. So finally we have Gm is equal to antilog of 1.20976 is going to be 16.2. So Gm is 16.2. Let's come to merits first. First one, it takes into consideration all the items. Second one, it is a subject to algebraic manipulations. Third one, it is of extensive use when dealing with ratios, rates, percentages, etc. Also, let's see some of the demerits. The first one, it is not generally understood. Second one, it is difficult to calculate. Third one, it cannot be determined when there are both positive and negative values in the series, or where one or more of the values is 0. Geometric mean is especially useful in the following cases. First one, the most useful application of geometric mean is to average the rates of change. For example, from 2006 to 2009, prices increased by 6%, 11% and 16% respectively. The average annual increase is not 11%, that is the 6 plus 11 plus 16 divided by 3 as given by the arithmetic average, but it is 10.9% as obtained by the geometric mean. This average is also useful in measuring the growth of population because population increases in geometric progression. Second one, geometric mean is theoretically considered to be the best average in the construction of index numbers. It makes the index numbers satisfy the time reversal test and gives equal weight to equal ratio of change. Third point, it is an average most suitable when large weights have to be given to small items and small weights to the large items, situations which we usually come across in social and economic fields. The harmonic is primarily used in averaging rates. It is defined as a reciprocal of the arithmetic mean of the reciprocal of the individual observations. In other words, the harmonic mean is the total number of items of a variable divided by the sum of the reciprocals of the values of the variable. So thus by definition we have the formula to calculate harmonic mean. Harmonic mean is represented as HM. HM is calculated as capital N divided by 1 upon x1 plus 1 upon x2 plus 1 upon x3 so on till plus 1 upon xn. When the number of items is large, the computation of harmonic mean in the above manner becomes tedious. To simplify calculation, we obtain reciprocals of the various items from the tables and apply the formula. In case of individual series, harmonic mean is calculated as n divided by 1 upon x1 plus 1 upon x2 plus 1 upon x3 so on to plus 1 upon xn. This is equal to capital N divided by sigma of 1 upon x. In case of discrete series, harmonic mean is calculated as n divided by sigma f times 1 upon x. So that is equal to n divided by sigma f by x. In case of continuous series, harmonic mean is calculated as n divided by sigma f times 1 upon m. So that is equal to n divided by sigma f by m. In individual series, harmonic mean is computed by applying the following formula. We know the formula for harmonic mean in this case is going to be n divided by 1 upon x1 plus 1 upon x2 plus 1 upon x3 so on to 1 upon xn. So this gives us n by sigma 1 upon x. x1, x2, x3, etc. These refer to the various items of the variable. Now let's see an example here. Calculate the harmonic mean of the student marks of examination in the year 2009 to 10. Now let's see the solution to this. So let's calculate harmonic mean using the formula here, n divided by sigma 1 upon x. So we have calculated sigma 1 upon x equals to 0.713 and we know that n is 8. So we are applying the formula, so that is equal to 8 divided by 0.713, which is equal to 8000 divided by 713. So that will give you 11.22. In discrete series, we know harmonic mean is computed by applying the formula as harmonic mean is equal to n divided by sigma f times 1 upon x is equal to n divided by sigma f upon x. So the steps involved here are: first one, take the reciprocal of the various items of the variable x. Second step, multiply the reciprocal by their respective frequencies and summate the product, say star. Third one, divide the total number of frequencies n by the coefficient resulting by the star of the above point. Now let's see example. Calculate the harmonic mean of the following data given below in the table. Now let's see the solution. So we have done the calculation here in the table, and through the table we have found out that sigma f times 1 upon x or sigma f by x is 5.975 and n we know is 120. So now let's apply the formula. Harmonic mean is equal to n by sigma f times 1 by x, that is equal to n divided by sigma f by x. So this is equal to 120 divided by 5.975, which is equal to 20.08. In continuous series, harmonic mean is computed by applying the following formula. Harmonic mean is equal to capital N divided by sigma f times 1 by m. So this is equal to n divided by sigma f by m. So the steps involved here are: the first one, replace the classes by their mid values m and find out their reciprocals. Second step, multiply these reciprocals by the respective reciprocals and summate the products, say star. Third point, divide the total number of frequencies n by the coefficient resulting by star of the above point. Now let's come to the example 11. Calculate the harmonic mean of the following data. Now let's see the solution to this. So using the table, we have done some calculation here, and out of the calculation we find that sigma f times 1 by m or sigma f by m is 3.3 and n we know is 50. So let's apply the formula. Harmonic mean is equal to n by sigma f times 1 by m is equal to n by sigma f by m. So that is equal to 50 by 3.3. That will give you 15.15. The harmonic mean is restricted in its field of usefulness. It is useful for computing the average rate of increase of profits of a concern, or average speed at which a journey has to be performed, or the average price at which an article has to be sold. The rate usually indicates the relation between two different types of measuring units that can be expressed reciprocally. For example, if a man walked 24 km in 6 hours, the rate of his walking speed can be expressed as 24 km by 6 hours, that is equal to 4 km per hour, where the unit of the first term is a kilometer and the unit of second term is an hour. Or reciprocally, 6 hours by 24 kilometers is equal to 1 by 4 hours per kilometer, where the unit of the first term is an hour and the unit of the second term here is a kilometer. Let's see merits first. First one, it is based on all observations. Second, it is most appropriate when more weights are to be given to small values. Third one, it is not affected by the single extreme item in a series. Fourth one, it is adaptable to averaging rates of performance. Fifth, it lends itself to algebraic manipulations. Now let's see some of the demerits as well. First one, it is complicated and difficult to comprehend. Second, it greatly magnifies the importance of small numbers and thus has a limited scope. Third one, it is meaningless when the observations include both positive and negative values, or when one or more values are zero. The certain definite relationships exist among the various measures of central tendency. In any distribution, when the original items differ in size, the values of AM, GM and HM would also differ and will be in the following order. AM will be always greater than or equal to GM, that will be always greater than or equal to HM. That is, arithmetic mean is greater than the geometric mean and geometric mean is greater than the harmonic mean. The equality sign hold only if all the numbers x1, x2, x3, so on, xn are identical. Also note here, for two numbers we can have the relation as geometric mean square is equal to arithmetic mean into HM, harmonic mean. Now let's see an example here. Find arithmetic mean, second geometric mean, third harmonic mean of the numbers 6, 10, 3, 4 and 2. Now let's see the solution. We have 6, 10, 3, 4 and 2. Let's calculate arithmetic mean first. So arithmetic mean is x bar is equal to sigma x divided by n. So let's calculate that. 6 plus 10 plus 3 plus 4 plus 2 divided by 5. So this is all the summation is equal to 25, that is divided by 5 and it will give you 5. So arithmetic mean is 5. Now let's come to the second part. Let's calculate geometric mean. We know the geometric mean is given as nth root of x1 into x2 into x3 into so on xn. So log of geometric mean is equal to log of x1 plus log of x2 plus log of x3 plus so on log of xn divided by capital N. So geometric mean is anti-log of log of 6 plus log of 10 plus log of 3 plus log of 4 plus log of 2, and this is divided by capital N, and which is 5. Now geometric mean is anti-log of 0.7782 plus 1.000 plus 0.4771 plus 0.6020 plus 0.3010, and the whole thing is divided by 5. So geometric mean is equal to anti-log of 3.1583 divided by 5. So again, geometric mean is anti-log of 0.63166. So that is equal to 4.2821. Now let's come to the third part. Let's calculate harmonic mean. We have the formula for calculating harmonic mean as n divided by 1 by x1 plus 1 by x2 plus 1 by x3 plus so on 1 by xn. So this is equal to n divided by sigma 1 upon x. Let's put up the values. Harmonic mean is equal to 5 divided by 1 by 6 plus 1 by 10 plus 1 by 3 plus 1 by 4 plus 1 by 2. So that is equal to 5 divided by 0.1667 plus 0.1 plus 0.3333 plus 0.25 plus 0.5. So that is equal to 5 divided by 1.35. So finally we have the harmonic mean as 3.7037. So finally we have reached towards the end of today's episode. We have learned today the meaning of arithmetic mean, its objectives and its types. We have also studied in the script the various kinds of averages such as arithmetic, simple and weighted, geometric and harmonic means. Merits and demerits of all these kinds of averages have also been discussed in the session. We have also learned about calculation of these averages in case of individual series, in case of discrete series and continuous series. Also, the script included the discussion on the relationship between these three averages: arithmetic, geometric and harmonic. So that brings us to the end of today's episode. We are ending here with half of the chapter, measure of central tendency, and we'll see you again discussing about the second part of this chapter on median and mode. Have a nice time. Thank you and bye.